Welcome to the Deep Dive, where we try to make sense of the big, complex ideas out there. Today, we're pointing our telescopes, metaphorically speaking, at Seyfert Galaxies,
hmm
real powerhouses in the cosmos.
They really are, and absolutely key for understanding how galaxies, well, how they tick. Seyferts are one of the main types of active galaxies, the ones with those incredibly bright centers.
Right, active galaxies, so like quasars.
Exactly, they're in that family. But with Seyferts, there's a crucial difference. While the nucleus, the core, is almost quasar bright, you can still clearly see the host galaxy itself. Often it's a spiral galaxy, just like our own Milky Way, but with this intensely energetic thing happening right in the middle.
Okay, so it's not just a single point of light far away, you see the whole structure. And our goal today is to dive into what's actually powering that bright nucleus, the AGN, or active galactic nucleus, and also tackle this interesting classification system they have. It caused a bit of a stir, I understand.
It certainly did. Yes, Seyferts are a huge subclass of these active galaxies. And you mentioned power. Even though they're usually closer and not quite as luminous as the most extreme quasars, the energy output from a Seyfert's nucleus is still immense.
How immense are we talking?
Well, think about this. The light from just that tiny central region, the AGN, can often outshine the combined light of all the billions of stars in the rest of the galaxy.
Wow, that's hard to picture.
It is, and it's not incredibly rare either. We think around maybe 10% of all galaxies fall into the Seyfert category.
So what's the mechanism? What's generating that kind of light and energy in such a small space?
It boils down to the usual suspect when you find extreme cosmic power, a supermassive black hole, an SMBH.
Right at the galactic center.
Precisely. But it's not just sitting there, it's actively feeding. There's a huge disk of gas and dust swirling around it, heating up as it spirals in. This is the accretion disk.
And that's the light source.
That's the primary engine, yes. The intense friction and gravitational forces heat that disk to incredible temperatures, making it blaze with radiation, especially very strong ultraviolet light.
Okay, so a black hole feeding frenzy powers the core. But you mentioned a classification puzzle. Initially, astronomers split them into type I and type II. What was that based on?
It was purely based on their spectra, the light signatures they emitted. When you break down the light, you see specific emission lines, like fingerprints.
And type I showed.
Type I Seyferts showed two distinct sets of these lines. You had relatively narrow lines, indicating slower-moving, cooler gas further out, but you also had these incredibly broad lines.
Broad lines, meaning the gas is moving very fast.
Very, very fast. Those broad lines suggest gas whipping around at speeds up to, well, maybe 10,000 kilometers per second?
10,000 kilometers per second. That's, what, 3% of the speed of light?
Something like that, yes. Incredible speeds, happening very close to the black hole itself. The broadening comes from the Doppler effect. Gas moving towards us is blue shifted, gas moving away is red shifted, and it smears the line out.
Okay, that makes sense. So that's type 1, fast gas, broad lines.
Yeah.
What about type 2?
And this was the puzzle. Type 2 Seyferts, they only showed the narrow lines. Both the permitted and forbidden ones were narrow. The signature of that super fast broadline gas was just gone, absent.
So wait, one type looks like it has this high-speed chaos near the center, and the other doesn't. That seems like a fundamental difference. Why didn't they just say, okay, these are two completely different kinds of active galaxies?
That was the initial thought, of course. But it led astronomers towards a really elegant idea called the unification scheme. The theory now is that Type I and Type 2 Seyferts aren't fundamentally different objects at all.
Okay. So what is the difference then?
It's simply our point of view, our viewing angle.
How does that work?
Imagine the central engine, the black hole, the super hot accretion disk. The really fast-moving clouds close in is surrounded by a big, thick, dusty donut. We call it an obscuring torus.
A cosmic donut. Okay. Made of dust.
Exactly. Now, if our line of sight to the galaxy happens to look straight down the hole of that donut,
We see right into the center.
precisely, you get a clear view of the accretion disk and that superfast gas in what we call the broadline region, or BLR. You see the broad lines, and boom, you classify it as a Type I Seyfert.
Right. But if the donut is edge-on, from our perspective?
Then that thick, dusty torus completely blocks your view of the central engine and the fast-moving BLR gas. It's obscured.
Ah, I see. So you can't see the broad lines because the dust is in the way.
Exactly. All you can see is light that originates from or is scattered by gas clouds further out beyond the torus. These are the slower-moving clouds in the narrow line region, or NLR. Since you only see those narrow lines, you classify it as a type 2.
So it's the same engine inside, just hidden in type 2s.
That's the prevailing theory. And the fact that we see intermediate types, type 1.5, 1.8, 1.9, where the broad lines are partially visible but maybe weaker, that really supports this idea. It suggests it's a continuous effect based on how much of the core is obscured by that torus.
That's actually a really neat solution. It turns two different things into just one thing seen from different angles. Very clever.
It unified a lot of confusing observations, yes.
So, stepping back a bit, what does the existence of Seyferts tell us about, say, the history of the universe or how galaxies evolve?
Well, that's where it gets quite interesting. We know that active galactic nuclei in general, including the much more powerful quasars, were significantly more common in the early universe. Billions of years ago, the cosmos was much more active.
So galaxies were feeding their black holes more vigorously back then.
It seems so. The fuel was more readily available, perhaps. The fact that we see so many Seyferts around today, which are active but generally less luminous than primeval quasars, suggests this kind of AGN activity might be perhaps a later stage or a smaller scale version of that earlier, more violent activity.
So it raises a question, doesn't it?
It does. Are the Seyfert galaxies we see scattered around us now basically the descendants, the modern-day, perhaps less energetic remnants of those incredibly powerful quasars that dominated the young universe? Or maybe just the smaller ones that took longer to get going? It's something we're still actively trying to piece together.
A fascinating thought. Are we seeing the embers of ancient cosmic fires? Something to definitely ponder.
And on that note, this deep dive was sponsored by embersilk.com. If you're looking into AI education or how to integrate AI, Embersilk is the answer for all your needs.
Absolutely. Check them out at embersilk.com. And thank you for joining us on this journey to the heart of Seyfert Galaxies. If you found this interesting or learned something new, please do subscribe to the show and maybe leave us a 5-star review. It genuinely helps get these deep dives out to more people. Until next time, keep asking questions and keep looking up.